So let me explain the model. Oh, doesn't work.
Quello è sempre nel pointer, ma è tutto controintuitivo, devi andare sui tasti che vanno
sì, devono fare.
La rovescia.
Ok. Tutto yeah. Pullback attractors here. So that, I mean, what we want to consider this. So this model we look at is a model which was suggested. I mean, Michael is somehow an honor, so Michael here, so suggested by a group of people in 2015. That's exactly somehow the one we choose and somehow try to study, because we're interested somehow to look at one model people use from a more applied viewpoint. But this is somehow they themselves draw on older traditions. I mean, this goes all the way back to Charney, Phillips. I mean, it's a kind of insight of the standard kind of model people use in this area if they want to do models of intermediate kind of complexity. And they wrote one version, and we just stick to this one just to be concrete in one way. So what we have is somehow we have a model for the atmosphere and we have a model for the ocean. And the aim of these kind of models is to have a model which is simple. Yeah, I mean, to put it's like a good caricature. Yeah, it should be similar to reality, but it should only catch somehow the essential feature of it and not be too complicated. So we don't want somehow the hyper-realistic painting which people painstakingly taking years to produce. We want to have a nice thing which is easy, and hope maybe we can say something as a mathematician about it. So there's somehow two essential simplifying assumptions. One is somehow the assumption of shallowness, so which will bring the system more or less in hydrostatic balance. And this is because we're interested only in weather systems on a very large scale, so think on a kind of global scale. And then another simplification which is done, that you work on mid-latitude where the rotational forces, the corrosive forces are very strong. So also somehow you're more or less in geostrophic balance. Not exactly, because then everything would be too much balance is not good, because then nothing would happen. So you need a bit of around, so you make what is called the quasi-geostrophic approximation. And the ocean is also simplified. Somehow you assume that you only look at what happens near the surface, and so we went up with five functions we have to put into our model. So in the atmosphere, in leading order, I said we have here hydrostatic and geostrophic balance, and this leads you to an equation of this type. And you see this is just the usual thing. You have there's a quantity which is transported, which is a Laplacian of something. So it's like an Euler equation in stream functions representation, but this is not the stream function. This is the quasi-hydrostatic pressure, which comes from you looking at all the kind of scaling things which are behind that. So this has a totally different meaning, or formally looks very different. And then you have somehow these kind of things here, which is somehow the extra things, which is coming from the density equations and somehow coupling things with the vertical motions. And the velocity is given in the usual thing by the stream function. So the structure is very analog, and we will use a separation G for somehow the nonlinear term in the usual way. Okay, and so we end up with this somehow, let's say this basic equation, and then you put some decorations on it to make it more interesting. So you need a better plane approximation, because it's important for the application to have somehow the kind of qualitatively right structure. And we need mathematically to put a bit more dissipation into the system. So we assume that the system has this kind of friction. So the physical, you may wonder about the double Laplacian. You have the double Laplacian because the physical variable and the vorticity is a Laplacian of the side. And so it's somehow the Laplacian of the physical variable, not the double Laplacian. It's just because of how you write it. And but you know, so now I'm going forward. So I said this better plane, and then somehow this is somehow this viscosity is eddy viscosity. So the problem what you have in the equation is that you have here this kind of we have this omega which you don't know. Yeah? So you can't solve this equation because you have one unknown too much. Okay, so you need another equation, and so that's you introduce somehow some thermodynamics to your system, and here you see somehow what you already saw in Julia's talks. This is this kind of radiation term, incoming, outcoming radiation, blah blah. It's exactly the same kind of thing. And here somehow the temperature is flowing with the fluid, and it's done here with somehow the middle layer, because somehow I didn't say this before. I approximate also in depth. I have only 2 density layers to make the system simplified, and you need at least 1 layer is not enough. 2 layers is somehow the minimum you need to get away to get the baroclinic instability. So that's why you take 2. 2 is the minimum. And okay, as a mathematician, you can take n, doesn't make a difference. But okay, but we have already enough of variables. And so then the thing is actually temperature is living at the surface between the 2 layers. And that's on here, and you see somehow the omega appears here again. Oh, beautiful. Now you have another equation, you get rid of the omega, but you got another variable, so you have a problem again. Okay, but then somehow if you do the case scaling carefully, then you recognize, okay, you somehow, Julia talked about this, so you have somehow this kind of friction terms between the to break things a bit down. You have all the radiation terms, this is the incoming radiation. And then using the scaling analysis, you can actually see that you have the relation between the temperature and between the baroclinic stream function, and now you close the set. And that's somehow the classical 2-layer quasi-geostrophic model for the atmosphere. And because we want to have a kind of an ocean model, you can add an ocean model, which is also again a kind of quasi-geostrophic thingy which you write. And so it's a bit different because you assume that you have only 1 layer, the lower layer is somehow at rest. You have some kind of extra friction with somehow the bottom of the things, which is breaking you down. And you have also a kind of to get somehow this kind of nice radiation balance with your core. You have also temperature of the ocean, obviously, because you have incoming radiation, you have to take care of that. And this part is essentially somehow like Julia said before. Okay, and so we end up with this slight monster here. So these are somehow all the kind of equations we look at. So, and so I made a kind of caricature. So what you have to imagine, you have somehow you're in the mid-latitude, somehow here of the ocean, and then about this 1 layer of the ocean, there's the ocean and the temperature of the ocean, they're living on the surface. And we'll explain afterwards that essentially you have a continent somewhere at the date boundary, so you can't flow around like this. But on the atmosphere, you have 3 layers, somehow two layers, to wind layers, and 1 where you have somehow the temperature in the middle. And the radiation is coming from the top, and then you have somehow radiation going in and out between all these kind of things, and you just take balance of this. This is nothing particularly surprising. And so you have, essentially, it's interesting because it's a marriage of 2 models. Somehow the two-layer quasi-geostrophic model, which somehow all the things in the blue, if you take all of them and with this, and a lot of people already from a mathematical point of view looked at it. So these are only mathematicians. I mean, there's an infinite list of people in metrology to look at this model. So this is somehow only people who did some kind of mathematical works about it. And then it's exactly what Julia talked about. If you take the red ones, then you end up in the model that Julia presented you. And so it's somehow exactly the marriage of these two models together. So and then, so here's a bit of the boundary condition. So in the atmosphere, you can once go around because that's somehow the thing you want. You want to have a jet somehow which is go around. In the ocean, you have nothing like that. And on the top, on the bottom, in the atmosphere, or on the boundaries, you have to say what is happening. And you say nothing can flow out of it. Yeah, so that's because then you don't know what to do if it's different. Okay, so so far so good. I mean, that's somehow how we define the operator. Maybe I skipped that. And so then you can do somehow, you can try to make an estimate on the energy. You just massage a bit, and the thing is somehow made that you get a nice energy. So you see somehow, you see the kinetic energies of the dynamical part. You say here's some kind of energy which is coming from temperature, and that's something which is related to the deep ocean. Then the friction is your friend. They give you some kind of damping terms, and the radiation is also your friend because it also gives you some kind of damping terms. So this somehow is stabilizing this kind of system, and then you get here some rubble on the other side. Okay, now you can show, and then somehow the first thing you have to ask yourself, does you have actually a solution? And okay, and then you get somehow, you can do the usual kind of theory you do for Navier-Stokes, and then you get somehow this kind of regularity. And this is somehow, there's nothing new about it. You have to keep in mind that the variable is the stream function. We look at physical variables, the velocity. So if you take somehow, if you subtract everywhere 1 order of derivative, you see that this is somehow what you always get. So there's nothing surprising there, except for the ocean temperature. where you somehow have a bit less of regularity, but you get some nice thing because of the height of the radiation force. This gives you some high power. So this is actually helping you. It's not a bad thing, it's a good thing. We like it to have it. Yeah, but the problem is it will be not as regular as the others because you don't have the double Laplacian in the equation, because here you don't have the physical variable, it's TO, not the Laplacian. So this is less regular. Okay, and then you can go, I mean, the first thing you need to do for sanity is somehow weakness, somehow uniqueness. And so the only real troublemaker which are different, which one hasn't treated before, is somehow terms of this form. But as I said, you have to remember the temperature of the atmosphere and the stream function of the atmosphere, they're related by a linear relation. So it's an H1, so it's an all LPs. So this is beautiful, yeah, there's no problem. We have enough estimates. The problem is for the ocean temperature, there you're in trouble because the ocean temperature is only in L2. So if this is the ocean and this is the atmosphere, you're in trouble. The one where it's both ocean, it has a sign, yeah, that's a good thing. So that's helping, it's a good guy. The problem is where you have mixed ones, because then you don't know the sign. And so after some careful estimation and working a bit around it, and this here is actually surprising, this model is better than the EBM model. So it's actually easier. In the EBM model, we had to worry about somehow L4 spaces and so on. Here you have somehow more or less a classical uniqueness, and you get uniqueness. And then you can also go further on to more general solutions. And then we try to look a bit, somehow get a bit of more structure of the system. So we can associate then a dynamical system to it because of our solution, semi-dynamical system, because of the Laplacians, and we can show that we have actually an absorbing set, which just comes from the higher kind of stability estimates, like for Navier-Stokes. So you get, and from this one you can get some kind of compactness. If you have, and I didn't stress this before, if you have this kind of extra condition, so that's something which, so in the model you have this kind of setup of the temperature, and you have to put them in a very precise way. Otherwise, this doesn't work. And then you can show that you have you get a kind of, you get a global attractor of the systems. You can repeat all the analysis. Then if you carefully go on, you can show that you also, this attractor will be actually finite dimensional, like for Navier-Stokes. So this is somehow a similar analog result. And you can get the radius of the attractor, which is a bit unphysically large. But this is also somehow like it always is. Yeah. Now then we looked at determining modes. So I mean, so what is you look at some functions, and these functions have this kind of some property that they improve you the Poincare inequality. And so for example, just think about this LJs are just as a first n Fourier modes, just for simplicity. But you can do other things. You can look at some points where you know things, or other kind of objects you want to look like, which somehow fix you the low modes, so that you can improve somehow the constants which you have here in the Poincare inequality. And then you can show that that you can find an epsilon, so that you can make so if you have every epsilon, you can find an L. Now for the Fourier modes, this is somehow obvious. You can do that, and somehow you can show that you have two solutions, and these two solutions somehow only looked at on these functionals asymptotically don't differ, then the solution will be the same. So the point is essentially that you need to look at finitely many coordinates to be able to slave everything to it. Yeah? So this is somehow another way of expressing the essential finite dimensionality of the thing. The interesting thing is here that we don't need to control here the ocean temperature. So this somehow comes automatically. So the ocean is somehow more slave than the others. Yeah? You don't need to observe it. I mean, if you know what the others are doing, the ocean has to go along. It has no other choice. The temperature of the ocean. But this depends on the parameter range. For the physical parameter range, this is true. And then the last thing which we try to attack is somehow to show that the temperature should be non-negative because it's in Kelvin. And so for TO, we can do that. We just use the classical theory of invariant regions, and doing that, you get exactly what you want. But the problem is we can't do it for the atmosphere because we have the problem. We have two problems. We have So you can do it. I mean, if I ignore this term, then I'm back to what Julia has done more or less, and then we can easily show that that you have this property, or you can do it if you kill the thermodynamical terms. You can also do it, but you cannot do both of them together, because I mean you do different tricks in both cases, and somehow they don't work if you have both of them. Yeah, so they're somehow in a contradiction to each other. So we need some help. Yeah, so somebody knows any kind of techniques one could try to throw at it. I mean, it should be true, but I don't know. I don't know why. Okay, and so so what we have done so far, we show existence and uniqueness of a weak solution. We show also continuous dependence on initial condition and parameters. I didn't really represent this. I just jumped a bit over it. So what I said, we have the existence of attractor, finite dimension. We have existence of data mining modes, and so we put somehow the kind of the standard things you can do for deterministic systems. So next thing would be go to a kind of stochastic version and somehow try to, we are working on this, and so it's partially done, a stochastic version, and try somehow to go for existence uniqueness of the invariant measure, show response theory, and try somehow to see that also in this case you have somehow this kind of control of the climate you would like to have, because I mean the invariant measure is the climate you want to compute in some sense, and so you would like to have that this behaves nicely under perturbations and stuff, and then somehow obviously questions start, perturbation of what, under what variable it behaves well, blah blah. So then you have a lot of parameters you can make a derivative with respect to, so you can spend a lot.
Very nice. There is room for questions.
Is there a numerical code then to make? Are you aware that there is some possibility of making numerical simulations already?
MA1. It's MA1.
Ah, okay.
This is just MA1. Straightforward. So there's a code. The answer is, so there's a code, you can download it from the website. So
it's already available.
That's exactly what we did. That we choose exactly that.
Thank you.
Yeah.
I have wondering, when you proved the existence of the attractor for
Yes.
PDA, what do you mean for attractor for the PDA? You mean
The global attractor.
a global attractor, but it's a unique piece, so you have also topological transitivity, or is minimal the set you show? I was not clear.
So it is.
Because
it's
if
a maximum.
you have a finite dimensional dynamical system,
Yes.
you must show that there is also topological transitivity, in the sense that the attractor is a unity.
Yes.
Unit. Yes.
Or it's minimal, it's more or less equivalent.
It is so.
What you?
It is not the okay. I don't know somehow so well the terminology of attractor in general, but what in this somehow what in the PDE context normally used is somehow it is a set which is somehow the maximal set which attract the maximal compact set which attracts all bounded set, and the minimal. Sorry, it's the minimal one which attracts all the bounded sets, and the maximal compact invariant one.
Okay.
So I think we don't
But
know
this
that.
does not.
We don't know it's unique.
It is unique.
It's not unique.
It is unique.
It is unique.
It's always unique.
Okay.
Per
We don't know
definition,
that it's
the
not-
definition is both.
Yeah.
The problem is that it contains
no,
all the
forward,
unstable
not
manifolds as well. Yeah, so this is somehow the maximal. This is somehow another definition is the set of all accumulation points of pure dynamics. So it means it contains a lot of things which numerically you will never see, because they are somehow the unstable things. So it's somehow this is a big net. It takes everything. It's not the thing you're really interested in, which should be much smaller. Yeah.
You would see it, the projection on the stable numbers. Just like a sort of SRB. Maybe.
No. No, I don't think that we know. We don't have. I don't know that. We don't know that it's not. We don't know that we have this kind of structure. It is essentially, you know only that any bounded set will go there, and
And you don't even know the convergence, the speed of convergence to this attractor.
No,
No.
I don't think so.
no.
You don't, I don't think
But
you need to know.
you guess that, do you guess that it's exponentially fast, should be exponentially fast as a guess, or?
No, it should not.
Should not.
Because it depends what you mean. Yeah.
Sorry.
There's a flow direction. No. There's a time direction, so that might kill there are some subset.
All right, I'm sorry, the pullback attractor is unique when it exists.
Yeah.
The forward one isn't. And we
But it's
have
a problem.
numerical evidence. We have numerical evidence for non.
Okay, we are going
It's a different attractor. It's a different attractor we're talking about. It's a different object.
It is good for the discussion.
Yes, we have to have a
afterwards.
discussion afterwards.
And
I can explain. I mean, that's a three-line proof to uniqueness. It's a banality. But it's the banalities in the definition. So it's a different definition than you think it may be.
No, so.
We'll continue tomorrow.
Okay.
And we have to go.